So good morning, everybody. So thank you for attending my talk. And today I'm going to talk about how to build a hyperscale cloud native SDNs and with Kubernetes. I am Liguang. I'm a senior principal architect from Futurewei Cloud Lab located at Bellevue, Washington. Futurewei Cloud Lab is a industry R&D lab focused on multiple spectrum in cloud computing research and engineering. Mainly on cloud compute, storage, networking, and AI. I'm a networking guy, so today we're going to talk about one of the networking project in my teams, and which will be a cloud SDN. So SDN is actually not a new term, right? It's a term which is well established. So in this talk, I'm going to first go through the motivation and of this project with the challenge emerge in the cloud areas, and also go through the architecture, our architecture, as well as a component snapshot. And then we talk about our strategy to integrate with OpenStack and how to integrate with the OpenStack Nova, OpenStack identity structures, and then we provide the performance comparison side by side with OpenStack Neutron. Basically, we are a Neutron replacement. And then I'm going to briefly touch upon how to conduct a large-scale test powered by another Cloud Lab project, networking project called migrate. And last, we're going to give a conclusions. So first of all, SDN, right? Software-defined networking has been well established, I think, over the past decades, and also since it has been widely adopted by enterprise networks, telco service provider, and even cloud provider to basically to improve the efficiency of the infrastructure and operations. And by offering centralizing control, I think network provider do enjoy the benefit provided by SDN. For example, they do enjoy the flexibility, programmabilities, as well as openness and smartness or intelligence, let's say. So SDN now enable network provider with the tool to optimize their network infrastructure, which is never seen before. But with the new there's a lot of new challenge emerge in the cloud areas. So mainly is on the scale and the complexity of cloud networks, which I'm going to talk about in more details in next slides. But in high level, we're going to see higher requirements on availability, reliability, as well as scale, latency, as well as throughput and concurrency. And here is a diagram which basically showcases the typical cloud networking setups. So you will see we have an underlay on the bottom. You're going to see we have an underlay network, which consists of a huge number of compute nodes or storage nodes, basically physical machine, and also as well as network device, mainly network switch, router, firewalls, and all those devices and compute nodes are connected by high-speed fiber cables. And then on top of this underlay network, you're going to see there will be at least one layer of overlay. Here, let's just to be simple, let's make just one layer of overlay, which will allow end user to basically define their own network resource, their private network in the cloud. And then within this private network, private virtual network, user will be allowed to create their own network resource. For example, subnet, port, and also define the association among these resources. For example, the routing rules, routers, security group, and even network echo, etc. So let's not go too beyond, right? Let's just keep a very simple, simplified setups for two-layer setups. And you see on the right-hand side, there will be the corresponding network control plane for the cloud. And on the top, you will see there will be a virtual cloud, virtual network regional controller. And on the bottom, you see there will be a local network agent deployed in every single compute nodes in the cloud, in a cloud region, basically. So, and what the regional controller responsibility is, they will expose API to end user and allow end user to create and manage a bunch of cloud network resource, for example, VPC, subnet, port, security group, etc. And then the controller going to program it, basically send down through the southbound, if we talk about the SDN terms, to every single agents deployed on the local host. So that would be the main ideas. So the challenge for cloud network is quite special. It's not only on the complexity, but also on its scale. So if you see the underlay network, here we are not talk about a few thousands of compute nodes. Here we're targeting on hundreds of thousands of compute nodes or even millions of compute nodes in the cloud region. That's one challenge we are facing. Second challenge is in the overlay network, can you support multi-tenancy and allow, let's say, a very large number of VPC deployed in a region, let's say millions of VPC. And in some cloud VPC, we will have some huge like deployment. For example, a giant customer comes say, hey, I do want to deploy 1 million VM virtual machines inside one single VPC. So combine these two requirements, we are envision that we need to support in the order of 100 millions of network resources in combined in a single region. So that will be a large number. And not even mentioning that these network resources are actually tightly coupled together. So a port has relationship with security group, with routing rule, etc. Right? So those resources actually not independent, they are tightly coupled. So how to handle such a complicated resource management task in the cloud? That's challenge 2 and 3. And I will briefly talk about the last two challenge is the high availability for cloud SDN control plane. So cloud SDN control plane is responsible for exposing API to serve end user, right? So if the control plane, the controller is down, then the end user deployment going to get impacted. So they will raise a lifecycle ticket, for example. So this will be painful for end user and for cloud provider as well. So how do we keep high availability? When we talk about HA here, we're talking about 5 nines or 4 nines or even 4 nines or even 5 nines, etc. So this will give cloud provider a very little margin for, like say, for doing things wrong. For example, if you talk about 5 nines, then you only have about 10 minutes downtime buffer in a year. So, and the last will be ultra low programming latency. So giving such a complicated network and the scale, but end user is still expect the network configuration can be programming down to the end host and make it effective within a matter of seconds. For example, some new user workload container serverless, they have very high requirement on programming latency. So with these 5 challenges.
Can I ask a question quickly?
Sure, go ahead, please.
This slide, are you referring to what a cloud provider needs to use like public cloud? Because for the end user, the underlay is not visible.
Exactly, yes.
So this is the control plane for a cloud provider.
That's a good question. So the control plane is actually for the overlay, for the virtual network controllers.
But is any of this visible to an end user?
The control plane, the regional controller here, has API exposed to end user. So this is different from the underlay controller, for example, ODL, the role ODL play maybe. Yeah. So here, with giving these 5 challenges, we believe we need brand new solutions that can leverage the latest cloud native trends to solve the scalability and complexity problems. And given that we introduced a new project called Arcos, it's a cloud-native SDN project designed from ground up by Futurewei, and we have the GitHub link here. So a few, I would say, architecture key points here is, first of all, because we talk about a lot of different kinds of network resource, right? So by decoupling those network resource and have a building a new network modelings. And we also we introduce a cloud microservice-based architecture. And basically, each microservice manages its own network resource. So by doing so, we can enable horizontal scaling for each individual network resource and APIs, and also allow fine-grained resource management. We also talk about the workload optimization programming, which means that inside the network control plane, we have multiple different programming paths, mainly the gRPC fast path and the message queuing scale path, which will allow our control plane to handle different user workload in different way. For example, if we have a customer asking, okay, I need to enable my deployment in a matter of seconds, which if we go with the regular way, that might not be possible. But with the gRPC fast path, we use a top-down network configuration programming, top-down from controller down to the network agents. This is fundamentally different from what OpenStack Neutron does. They basically adopt a bottom-up approach instead of a top-down approach. So with that, I'm going to quickly go through 5 layers in our architecture, which are resource management service, infrastructure services, cache database components, MQ components, and the last is the host network agent. So the top layer, the resource management service, includes certain microservices, and each microservice manages its own resource and scaling independently with its own database. Here we use Apache Ignite. And the second tier, the infrastructure service tiers, used to manage infrastructure resource, invisible to end user. So this is the layer which end user will see. Basically, for example, the node metadata manager manage all those compute nodes inside a cloud data center, which end user will not have no visibility to. So also we have another called data plan manager, which basically responds of programming down the network configuration to the end host, the compute nodes, and which is invisible to end user as well. And we have gateway manager, which basically handle cloud gateway services. With that, we also have a cache and database service. We use the in-memory database provided by Apache Ignite. And Apache Ignite basically is a distributed database management systems and for high performance computing. And Ignite used the DRAMs as the default storage and processing tiers, and it's super efficient in our opinions. And the host agent, we might not have enough time to cover the host agent, but we do have a lot of innovation in this domain because host agent, because it has to be deployed in every individual compute nodes. It got to be lightweighted because in the cloud, if you have a very heavy agent, you're basically eating up the resource supposed to use for the customer. So basically you are losing money. So you need to design a lightweighted, super efficient host agent to programming a large number of flows into the data plane. This is one of the component we probably don't have time to touch, but we can submit for future conference. So now we talk about OpenStack, and because we talk about Arcos is a new project. Why we need to mention OpenStack? Because OpenStack is a very comprehensive cloud computing platform offering the ICE functionality to create and manage private and public cloud infrastructure. So it's very well known, and it's modular design, basically provide compute, networking, storage, object store, for example, block storage, and dashboard, IDMs, identity service to end user. So this is a very, I would say, comprehensive ecosystem. So, but we do find a gap in the OpenStack ecosystem, which is mainly the networking services, Neutron. So on the bottom diagram, you can see that this is distributing tracings published early on by some of the researchers in Germany. In this diagram, may not be that in higher resolution, but you can briefly see that this is a data distributing tracing for a virtual machine deployment, and it involves multiple services, namely the Nova, the compute service, the Keystone, which is the identity service, and also Glance, which is the image service, and also Neutron and Cinder. So with that, you can see that the Neutron, the network service in OpenStack takes about at least 40% latency in a virtual machine creation. So, and this experience and this diagram actually is quite aligned with our testing experience. We see that in some high stress testing, OpenStack Neutron actually took more than 50%. So, which we will have more details result to talk about that. So our strategy, our open source strategy here is we adopt an OpenStack compatible strategy, which means all the Arcos APIs are OpenStack compatible to Neutron, basically. So what Neutron has, we has the same type of API, especially with all the fields, the API definition, etc. But we do offer some API which OpenStack Neutron doesn't have. And also we integrate successfully with the compute engine, which is Nova, identity service, which is Keystone, dashboard, which is Horizon UI, and CLI for all the major features. And with that, you can see that you can see this is OpenStack service list. We run OpenStack CLI, and then we list a bunch of services enabled in our test cluster. And you can see that OpenStack Neutron is still here, but it's disabled. And we introduced a new network type, Arcos, and we enabled it. And all the following tests is in these setups. And also we adopt the same benchmarking tool used by OpenStack, which is Rally. Rally basically is a very comprehensive tool and used widely by OpenStack community to conduct scalability and performance tests in various test scenarios. So we adopt Rally basically, and we use the same benchmarking tool, the same setups, and side-by-side compare with Neutron. And here is the some performance goal in the Arcos project. Basically, we want to provide 3 types of performance goals, including the latencies, throughput, and scalability. Latency, our goal is quite ambitious. Actually, we want to cut down the latency by 90%. Compared with neutrons, and also we want to provide a much higher throughput, namely 100x and 100x scalability compared with neutron. So here is some of the current status of our project. I'm not going to go through here, but instead I'm going to go through some of our test report, which showcase some of the key metrics, I would say key performance metric in this page, on this page. So including latency, let's talk about latency, right? Latency is actually quite, I would say, critical in a virtual machine deployment, because when you deploy virtual machine using OpenStack Nova Compute, which is the compute agent installed in every local host, need to trigger a bunch of API call into the Neutron service, and they will make 10 plus or even 20 plus API call. And if a single API call is slow, then the slowness actually will be exaggerated into 10x. So that's why we're trying to improve a single API performance for Arcos. So on the left-hand side, you will see that the Arcos can compare with Neutron, right? Can cut down 90% of the Neutron latency. And you will see that we tested multiple scenarios, mainly the VPC creation, VPC list VPC, also subnet and port creation and list. And with each test scenario, we have a few hundred or even a few thousand test cases and get the average and the tail latency. And you see that the red bar is Neutron and the blue bar is Arcos. So that's one thing. And this latency benefit is mainly due to the decoupled resource modeling and the distributed management by the in-memory database. So, and this is only on the API side, but on the right-hand side, it will be a full end-to-end virtual machine boot up workflow. And we compare the latency of the VM boot up. You will see that based on, and the y-axis will be the different concurrency level, meaning the number of virtual machines launched in parallels. So in the top, we launched 25 virtual machines and increase the concurrency level from 25 to 150 to 300 and all the way to 500. So you will see that Neutron's latency, even in a very low concurrency level 25, the VM boot up latency is pretty high, right? Can reach like about between 20 and 25 seconds, which is pretty slow. If we offer such a service, the customer may complain why your VM is boot up in so slow. And if you continue to look down, you'll see that in the 500 concurrency level, there's no data for Neutron because Neutron at the time already crashed. So later on, I'm going to give you another diagram, which is my preferred, I would say, diagram showing that the concurrency level for Neutron can only reach about 50. So beyond 50, you'll start seeing the success rate drop very fast. And also, we compare with the port, create, and update latencies for Neutron and Arcos under different RPS. And the x-axis is the throughput measured in RPS. And the y-axis will be the latency. And you see that in this corner, right, we have two curves present the latencies for neutrons. And you see that Neutron, when the RPS, right, reach about beyond 50, Neutron basically simply cannot I would say cannot sustain to such a high loads. But Arcos instead can continue to scale up to about 500. That is one thing. And this test has been conducted in the same, I would say, setup, meaning the same set of machines. So we use 3 powerful data center server to deploy OpenStack as well as Arcos, but we put OpenStack Keystone besides, because Keystone is quite, I would say, resource consuming, so we put Keystone aside. But that will be the same setup for the comparison test. And in the test, we run about 600, right? 600 iteration test, and each iteration we have 5 port creation and 5 port updates. And this is one diagram I'd like to show you, and another diagram, another say insight from this diagram. You can see that Neutron, if you see the latency level right here, when you see the latency at the level about 3 seconds, Neutron can only achieve about, the RPS is about 5 RPS, but instead Arcos can achieve 500 RPS. So that's another way of looking the throughput in comparison. And here is some details data showcase the latency distribution for Arcos when the RPS is pretty high, 300s. I'm not going to go into the detail, but we see that the average 25 percentile to 75 percentile latency of Arcos. And another similar diagram will be the port create and list latency. Port list latency actually is is very critical for VM boot up, because when a VM boot up, you need to call the port list API multiple times. So if we can, let's say, improve this API latency, that will help the VM boot up a lot. So you see that we pretty much achieve same level of performance improvement as compared with the last diagram. So here is an interesting performance comparison. Basically, what we do here, we're trying to push the stress test even further by saying that we want to see how Arcos can react when the, let's say, the very high VM put up concurrency level is triggered. For example, over 1,000 VM are launched in parallels. So you see that the on the left-hand side, we're seeing different number of VM launched in parallels. And on the top, we have about 500 VM launched in parallel. And on the bottom, we have 2,400 VM put up in parallel, which is quite stressed because we only have 19 compute nodes. And we launched 2,400 VM in parallels. And that will be the limit for the system, because beyond that, we are actually limited by the compute capacity. It's not limited by the network service performance limit. It's limited by the network, the compute capacities. So on the right-hand side, you see that the low profile and the system stabilities. Basically, you see that Arcos is quite stable during the test. And this is another diagram showing that, okay, basically another test. Basically, what we're testing is test how Arcos reacts when we try to create a lot of virtual machine and at the same time binding a large number of port or virtual NIC to the VM. In this case, we launch 500 VM in parallel, and for each virtual machine, we actually bind 10 ports to each machine, meaning that in total we have about 5,000 ports. And you see that that would be the latency numbers for VM put up under Arcos. And here is one of my preferred diagram. You see that this is a diagram clear so that the concurrency support by two platforms. The green curve is the latency, the success rate versus the concurrency levels for Neutron, and the blue one is for Arcos. And you will see that when Neutron can only reach about 100% success rate, only for concurrency level under 50s. If you go beyond 50s, you will see that the success rate, the BM success rate will dramatically drop down. And Arcos can continue to, the concurrency for Arcos is quite stable until about 1,000 VMs. And at the time, OpenStack Nova and OpenStack Keystone have some issues, and then we stop testing theirs. So this just showing you the concurrency comparison between these two systems, and at least we can show 20x concurrencies improvement compared with Neutron. And the next fun topic will be, okay, you keep talking about the performance goal for Arcos is to support 1 million of compute nodes and also very large VPC. But how can you conduct such large-scale test, right? This is, I think this is a common challenge for every cloud provider, because if you have one new network service, like network infrastructure service, you're trying to improve the performance and the scalability. One option is you have 1 million compute nodes for testing, right? But this is a challenge actually across the board. So what we are doing here is we have another project called migrate, which basically what we're trying to do, we're trying to conduct such an emulation framework and allow us to performance testing against multiple network infrastructure service, including Arcos. So here we have two options here. One is simulation, the other is emulation, right? Simulation is by modeling the network resource and the relationship among those resources. You can actually prove your performance to some extent, but the weakness here is not very realistic because you are actually not testing your code. You are testing the model, not the code itself or the service itself. But emulation, that's the approach we adopted basically provide a very realistic environment, but it's relatively hard to scale. And this is an ongoing project combined with Arcos. We want to prove that Arcos can be a real scalable environment, like say SDN controller, which support 1 million compute nodes as well as large number of network resource provisioning. And last tools, I think I have a few more minutes. I'm going to quickly touch upon the distributed tracing and modeling enabled by Arcos. So Arcos adopt open source project, a CNCF open source project called Jaegers and open tracings. And Jaeger basically is open source software for tracing the transaction between distributed services. And we use Jaeger for monitoring and troubleshooting the complicated microservice environment in Arcos. And you will see that on the right-hand side, this is a timeline view for Arcos. We can, for every API call, right? Here we enable it for 150 plus API, REST API. We can enable the tracing for on the API level or even down to the method level. And then we can trace the latency, the breakdown of the latency for each API. And also we can have a graph view for all the microservice that will be triggered, giving a network like a management API call. For example, if you create a port, you're going to involve multiple Arcos microservice. And this will be the view which give you a very detailed view at which microservice, how much latency has been taken at a given microservice. And here we have also leveraged another open source project called NetData to collect and also monitor the performance of our Arcos control plane. We can monitor control plane at various levels, right? From down to the pod levels, to the microservice level, and also to the host levels, multiple layers of monitoring. We also can zoom into every single microservice port and the infrastructure port, and we have a quite comprehensive metric like the compute, memories, IOs, network IO, storage IO, etc. We can have all kinds of a metric thanks to NetData. So with that, I'm going to conclude my talk. So what we are doing for the Arcos project, we're trying to build a scalable and performance SDN-based cloud virtual network control planes. And so to meet the new requirement raised by in the cloud areas. So, and we designed this SDN project from the ground up for the cloud, and a couple of key performance goals, including we want to support hyperscale, right? For millions of servers in the cloud regions, we want to enable ultra low latency, basically sub-second low latency for new container workload, and also we have high throughput and concurrency requirement as well. With that, I will say Arcos is an ongoing journey because if you ask me if we already achieved all of the goal, absolutely not. But we believe this is one step forward to meet the new requirement in the cloud domains. So, and with that, I will say welcome to join Arcos, and let's build a cloud SDN together and to be more scalable, performance, and extensible. And also, I would like to collect some of their feedback. For example, the user case in the telco network, for example, the user requirement, your architecture requirement, etc., or performance requirement. And yep, thank you. And maybe we have a quick 1 minute for a quick question. No? All right. So I use up all the.
You mentioned Kubernetes, right?
Kubernetes, yeah.
Where exactly do you sort of see the control plane interfacing with? Are you using Kubernetes as for the implementation of your control plane?
Yes.
Or are you controlling Kubernetes, right, in some shape or form, right?
That's a good question. So right now, the way is we use Kubernetes as basically we are a Kubernetes application. We are an application which can be managed by Kubernetes. But the other topic is, can we integrate with Kubernetes and use Kubernetes as a container orchestration platform, right? So we use as the network service provider. That's possible, actually. So right now we integrate with OpenStack for VM, but that's one pending topic for us is, can we integrate with Kubernetes? The answer is yes, but we haven't done that work.